Okay, the periodic law. This is chapter 5 in your textbook. It's there if you wanted as the resource. The beginning of today was mostly about the discovery of the periodic table. Okay, talk about the discovery of the periodic table. Tomorrow you'll have a sub. Okay, you'll have a sub. You'll have an assignment to do, and I don't know who y'all sub is in here for period tomorrow. Mask over nose. I don't know who it is tomorrow. And then Wednesday we will take our naming quiz, and we will do an activity Wednesday over periodic law. Okay. Actually, we'll do an activity on Thursday. Get everything kind of taken care of first. Okay. So next 3 days we'll be talking about the periodic law. Getting ready for your test on Monday. Okay, so the need for organization. Okay, this is our periodic table. In 1860, there were more than 60 elements have been discovered. At about this time, they were discovering approximately one new element per year. Okay, in the 1860s, they were discovering about one new element per year. But there was no organization for these elements. Most of the information was like written down like on a note card, a little index card. Everything they knew about the element, their mass, the number of valence electrons, its density, what it looked like, solid, liquid, gas, was all written down in a little index card. And that's how they kept up information of elements. Now we have a periodic table that has all that information on there. Okay, but the 1860s there was nothing. So in September 1860, the first International Chemistry Conference was held in Germany. Okay, to discuss this issue. This had started to become a problem. Professors were beginning to teach things, and there was really no way of organizing this stuff. It was nothing really coming out of it. Dmitri Mendeleev heard about the meeting. He actually went to the meeting. He was a very prominent, I would say very prominent, but at this point in time, he was a somewhat prominent scientist. He was a Russian scientist, and he went to Germany. He had studied in a couple other places. He had taught in Russia. He had went to the Heidelberg Institute and worked there. So he was somewhat known, and he was an organic chemistry teacher, and so some of this stuff was very pertinent to him. Okay, So he decided to organize the elements. Okay, he arranged his cards. The story is he played solitaire. Okay, he based his cards off of solitaire, and he had all these things. We know solitaire, you move the stuff around, and he saw a pattern. Now, a couple of things. He arranged them by increasing atomic mass. Similarities can be seen at regular intervals. Okay. Now, a couple of things about this is there were some problems with the masses. Okay. On the periodic at this time, the instruments weren't very good. You're talking about 1860s. You're talking about Civil War time. Okay. So just as a point of reference of technology, things like that, the masses of some elements, he said, were wrong, and in fact, they were incorrect. I said they didn't have the proper instruments to discover these masses. So part of the problem that made this so difficult is not all the data on there was correct. Okay. But he put them in masses. Okay. There were some exceptions. I saw them your homework today. That's the subject I just talked about. And you have to go look some of those up. Periodic, just the definition and pattern seen in the regular interval. So he arranged them by using here's a very key word here. Okay. The periodic table is arranged by properties. Okay. He ordered his periodic table off of atomic mass. Okay. That's a very key distinction between them. Okay. Very key distinction between them. He published this in 1869. Dmitri Mendeleev published, they say, in at least excess of 400 books or journal articles. Okay. Was a very prominent, at this point in time, was become very prominent in Russia. His father, who actually had died, his father was the head of a teaching university where he went. And so, he was kind of well known in Russia. And, he published a lot of stuff. Now, the question, that he was really asking, why could most elements be arranged by increasing atomic mass, but some could not? Okay, that was a question that he asked. And what was the reason for this chemical periodicity? So the answer to the question, that comes to that first question, okay, is Henry Moseley was kind of the next person we talk about. he decided that instead of ordering it by mass, he ordered it by atomic number. Okay, so I want you to get your periodic tables out. Your periodic table is ordered by atomic number. It's arranged by chemical property. I want someone to find me one spot where it is not. Now, our periodic table is mostly arranged by number and mass. Find me a spot on the periodic table in which it is not arranged by atomic mass, i.e. that means give me two elements that are sequential in which the mass of the second element is smaller than the element that comes before it. Go ahead. Cobalt and nickel. What's the mass of cobalt? And what's the other one? So there's one of them. Okay. There are multiple exceptions on that. Okay. So that's what Moseley did. Okay. Moseley just slightly modified Mendeleev's periodic table. Now there's a couple other ones on there that you can find also. What? Trillium and iodine. I did not know about that one. But yep, you were correct. Trillium and iodine would be another one. Okay. Very good. Those things. So that's what Moseley did, and that really answered the question. Okay, that could answer the question. It really goes back to. It really goes back to what Mendeleev said, is that these masses weren't correct in some instances. Okay. The periodic law, you can read those definitions there. It's arranged by properties. Okay, he was correct in his arrangement of properties, but not by mass. Okay. Now, how do we know it's not arranged by mass or arranged by atomic number? Is it a perfect block? No. Okay. So that's part of the reason why it is arranged this way for a specific reason. Okay. It's arranged this way for a specific reason. Now, there are things that we know now that we've already talked about: electron configuration, the s orbital, the p orbital, things like that, of why it fits in the way it does. Okay. But right now, okay, at this time in the 1860s, he did not. Now, there were some elements that he left blanks in. Okay. There were 8 at least. Kind of depends on who you want to talk to. There were at least 8 elements that he predicted existed that did not exist at that time. Okay. One of them being germanium. He called it eka-silicone. Okay. That was something he left that blank in there, and then went back and later, and once they found it, filled it in with something else. This periodic table was not accepted very well at first. Okay. It wasn't until really gallium was found, okay, in 1875, I think, when gallium was found. If you want to know what year something was found, you look in the back of the periodic table. Look at your back of your periodic table, and it tells you the discovery and the year and the scientist. Gallium was discovered in 1875 by in France, okay, whatever you want to say, okay. So we're really talking about a 6-year period where people didn't really believe everything he had to say. And that wasn't the only one. There was a couple of them, but if you look historically, gallium was kind of the turning point of, wait a minute, this man knew what he was talking about. Periodicity is because of the arrangement of electrons. We know this now. Your S block, your P block, your D block, okay? We now know this. In the 1860s, 1870s, they did not know that. So some things have been added. Okay, some things have been added. The noble gases were added. The noble gases were originally called what? Anybody know? The inert gases. The inert gases. Inert means non-reactive. Okay. You put an inert gas in something, you put in something that does not react. Okay. This is because they already have a full S and P block. Okay. Electrons. So they weren't really added. So this is 1975 to Strutt and Ramsey discovered argon in 1984, and then Ramsey discovered helium in 1985. It was very, these were very difficult to find because they did not react. Okay. And they were later changed. They were actually, I think, called, when they first discovered, were called inert gases. But we know krypton and xenon do form a few compounds, but helium does not, and neither does argon. Okay. The lanthanides and actinides were also discovered on the periodic table. Once again, it's arranged by properties, If it was arranged by atomic numbers, they would fit directly in there. Okay, that's why they're kind of shoved in at the bottom. This is review. This is a review. The S block. The S block are the two left-handed group 1 and group 2. They are very, very, very reactive. Okay, they're very reactive. Group 1 is called the alkali metals. Alkali metals. They are silvery in appearance. Okay, they are silvery in appearance. They are easily cut in half, and they are not found free in nature. I wish that I could still buy sodium. Okay, I wish I could still buy sodium. Okay, when most people think of metals, they think of something very hard, don't they? We used to have sodium, and did I tell you all this the other day? We talked about this. Well, Coach DeField, that's what he blew up his physical science lab over the elementary school. The middle school. He blew up his lab. If you go back, we used to have some here. We've used it all. If you go back, if you go look at Miss Collier's room, about right here, okay, about right here on the ceiling, you can look at the ceiling, and you can see where the ceiling's messed up. We used to have some sodium. I would take a spatula and I would cut it with a spatula, okay? And just pop it off, pop it off, pop it off. I put it in water and it blew up, okay? I went very small. The one time I had to break, put a really large piece in it, and you can actually see where the ceiling is frayed, where it messed it up, okay? So they're not found free in nature. Here's what I talked about again. We talked about this with sodium and salt, okay? But they are silvery in appearance. They are very, very reactive. The alkali metals are the most reactive metals. Group 2 are the alkaline earth metals. They are harder, denser, and stronger than group 1, okay? So they cannot be cut as easily as group 1. They are denser and they are stronger than group 1. They are less reactive than group 1, okay? They're less reactive than group 1. Where do we use alkaline? Where have you heard the term alkaline before? Batteries, okay? Alkaline batteries, you know. Well, you don't really use alkaline batteries as much anymore. They've gotten more effective. I'm trying to say when you were younger and things like that. So those are the first two groups. The third group is the D block. The third group is the D block. The next thing we're talking about is the D block. The group 3 through 12 also is transition metals. This is reviewed. They have slightly higher energy than the S block metals of the same period. 10 electrons, normally 2s. Have 2s and then 10s. There are some exceptions to this. This ones if you would have done on your test, you would not see. You would expect Ag to be 4d9, but instead it's really 4s1 3d10. Those are some exceptions to that, to the electron configuration. The D block is composed of nothing but metals. They are all good conductors, ductile and malleable. What does malleable mean? They can be shaped easily. They're easily bent. What about ductile? What's that mean? But ductile, what does that mean? That's luster. That luster is shining. Okay. What? No. Something that's ductile means it can be spun into a wire. Okay. It can be spun into a wire. And we know this, copper wire, okay, copper wire, it's very ductile. You can make different, you can make it, high gauge or low gauge copper wire or any type of wire. They're also very lustrous, okay? We know that these are very, very lustrous. Go back to malleable. Who has a class ring? Did you get any gold or anything put on that? Okay. Gold is one of the most malleable things. They can mash gold into, I don't know the exact thing, but very thin leaves, okay? Very, very thin leaves of gold. D blocks are notorious. Some of them are very, 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 very unreactive, okay? Gold, platinum, palladium are very unreactive, okay? We know this because you can just go get some gold, you can leave it there, and nothing's ever going to happen to it, okay? Now, copper, on the other hand, it can tarnish very easily, okay? Copper does tarnish very easily. That is a reaction, okay? That is a reaction. It does go away. No. Tarnish, It's kind of like, if you want to say it's copper rusting, yes, you could say that, but it's not rusting would actually be the correct term. Tarnishing would be the word. But it's kind of a similar process. These can be found free in nature. We know this. You can go get some copper wire. You can go get some titanium. Titanium is also very unreactive. The P block are metals, nonmetals, and metalloids. Here's the big thing to take away from this slide is the S and the P block are your main group elements, okay? When we talk next unit, we only care about S and P electrons. We only care about S and P electrons. So just stuff to talk about. Halogens are group 17. They are most reactive nonmetals. When Mendeleev actually started working with his periodic table, what started his thought process was he looked at the alkali metals and the halogens. He noticed they were both very reactive, and he found a lot of similarities in these two things, okay? And that's what really allowed, so that's really where he started. He started with the alkali metals and started with the halogens, put those together, and kind of fit everything else into his puzzle. They react vigorously with most metals to form compounds known as a salt. Salt is not sodium chloride. A salt, in the simplest definition, is the result of an ionic bond, with a cation reacting with an anion. Like, for example, when they salt the road in the wintertime, they don't go use table salt. They use ammonium phosphate. Okay, they also use beet juice. Okay, they use ammonium phosphate. Okay, it's a type of salt. In its simplest form, a salt is an anion or cation that are reacting together.
Why does that look like it's actually salt?
Because it's an ionic crystal. Just an ionic crystal. Depending on the size of the things, that's why you see like table salt has very small particles. Okay, each individual thing is a small thing. The bigger rock salt and things like that are not sodium chloride. They're a different one with the particles being a larger thing. Just things on there. We know this FCl are gas, bromine's a liquid. What's the only other liquid in the periodic table? Mercury. The F block, they are the lanthanides and the actinides. The lanthanides are the 4F. They are shiny metals. They are very similar to the alkaline earth metals, okay? That's what they're most similar to. The actinides are all radioactive, okay? Key thing about this is there are only 4 that are found free in nature, okay? From thorium to neptunium. So you're not going to go find Einsteinium in nature. That can only be made in a lab, okay? That can only be made in a lab. All right, and so that's what we're going to end today. Einsteinium is on there, yes, ma'am. I believe it's 99.